Hi everybody, today we'll be talking a little bit more about the nucleus and what goes on inside the nucleus, specifically looking at some of the changes that take place, like fission and nuclear fusion. We'll also be looking at the fundamental forces that go along with the world and with the inside of atoms specifically, and we'll also be looking at the subatomic particles that are present within atoms. So first one to talk about would be nuclear fission. And nuclear fission is a very important process here on the planet. But nuclear fission is when you take a large atom and it gets broken into smaller atoms. It actually gives off lots and lots of energy because as the mass goes down, some of that mass is actually converted into energy. And that energy is important because a lot of our electricity on the planet is generated through nuclear power plants, and those nuclear power plants are fission reactors. As an interesting fact, here in the United States, almost 30% of our energy comes from nuclear power. In a country like France, almost 75% of their power is nuclear power. So understanding that nuclear fission gives off a lot of energy is surely an important part of our world. Where does the energy come from? Well, it comes from the breaking of the nuclear bonds. When you break and form nuclear bonds, those things are very, very, very strong. They're, like it says, there's almost 100 million times stronger than chemical bonds. So obviously, we can get energy out of chemical reactions. We can get energy out of a nuclear change also. So what we're going to look at here is having some uranium-235 undergoing a nuclear fission. So uranium-235 is fissionable material, which means that if it absorbs a neutron, it can actually undergo a nuclear fission. So it says that here that you have uranium-235 hits by a neutron, it absorbs it. The atom decays into 3 neutrons and a barium-141, and we want to figure out what the other atom is going to be in this nuclear fission. So this is already here behind me. So it says we got our uranium-235. It has a mass number of 235. The atomic number is 92. That's going to absorb a neutron. So we just denote that with an N, 1 and 0, because the mass is 1. Obviously doesn't have a proton. And obviously when this goes together, we're going to add these. We're going to get a 236, and 0 and 92 is obviously 92. When we get this middle part here, well, really what that is, it's a high-energy uranium. And what it's going to do is it's going to undergo a gamma decay because it just gives off energy. You can look at the next slide if you want on your own. It gives some more information on that. Really just a fancy way of denoting a high-energy uranium atom. Well, that's going to undergo a decay in turn and give us some bariums. So barium-141, and then it says 3 neutrons come out of that, and well, what's going to be left? Well, we have 3 neutrons, so it's really 3 times 1, so there's really a mass of 3 up there. So we have 141 and 3, and 56 and 0. So we can erase that because we can actually figure out what that's going to be. So on the bottom, if we take 56 and subtract it from 92, we're going to get a 36. And if we take our 141 plus 3, which is 144, and take that away from 236, we're going to get 92. And we can look that up on our periodic table and we can see that the element with atomic number 36 is going to be krypton. Okay? So that would actually be our nuclear fission change that would take place, and that's what would be going on inside of a fission reactor. That's one of the pretty common reactions that's actually going to be taking place there. So anyway, obviously a lot of energy would come out of that too. We're not denoting that there, but that's what a fission. That's what a fission reaction would actually look like. So this is the slide I was talking about. It's in the notes if you want to spend a little bit more time looking at it. All right, so what a nuclear reactor is, you've probably heard of nuclear reactors before, but it's really just fission where you have a chain reaction taking place, where large atoms like uranium end up undergoing fission. How do those things keep from getting out of control? Because you've probably heard of that before. Well, there's things called control rods, like it says right here. Control rods actually absorb neutrons, and they allow it to keep the reaction from happening really, really, really fast. And what nuclear reactors are looking for is they're looking to have basically 1 neutron reacting at a time. That's called a critical mass. Have you ever heard of the term reaching critical mass? Well, that's when you have a nuclear power plant that's running at its correct reaction. Supercritical masses are what they don't want. That's when you actually have nuclear meltdowns and nuclear tragedies that can happen in a nuclear power plant. So anyway, just keep in mind nuclear reactors are actually fission reactors, and they're kept in that chain reaction is kept under control by a control rod. There's lots and lots of videos about nuclear things and nuclear safeties. This is one if you'd like to go watch it. You've probably heard of a couple nuclear disasters. There was 3 Mile Island. There was also Chernobyl, and most recently there was Fukushima in Japan. So there's lots of good information out there on those if you'd like to look at any of them. But by and large, nuclear power plants have been quite safe. But when there's a problem with them, the problem is very, very, very large. Nuclear fusion, you may have also heard of. Nuclear fusion is when you take 2 smaller atoms, or nuclei if you want to think about them that way, and you put them together to get a bigger one. It also, the total mass decreases because it gives off lots and lots and lots and lots of energy. On Earth, we don't do nuclear fusion because you have to put in more energy than we're actually able to get out of it. So that's one of the things that you need to understand, that fission is what takes place on Earth. It's the stuff that we can get energy out of, but it doesn't take place on Earth when you're talking about nuclear fusion. However, if we could have nuclear fusion, that would be pretty awesome because you could get a lot of energy out of it. And the stars, the sun specifically, is something that ends up having nuclear fusion taking place. There's obviously a lot of energy there. In the sun, what's happening is you have hydrogen that's getting fused into helium. And you can see here that in a star, you got this lots of different ranges. There's hydrogen fusion, then helium fusion. The atoms keep getting bigger and bigger on your way in here. And at the very center of the star, there's actually iron inside of that. So when you think about fusion, there's lots of energy there, but it's not something that we use on Earth at this time. So continuing on, talking about some of the fundamental forces and elementary particles that make up our world. The fundamental forces, there's 4 of them. Some of these you may have heard before, and a couple of them you probably haven't. You got the strong nuclear force. There's the electromagnetic force. There's something called a weak nuclear force. And then there's the gravitational force. I suspect we've all probably heard of the gravitational force before. The other ones maybe not so much. So the first one, the strongest of the ones here is the thing called the strong nuclear force. That's one that's pretty darn important to us because it's actually what holds atoms together. It actually holds the nucleus of the atoms together. It doesn't affect the electrons, it doesn't affect the chemical properties or anything like that, but it's the thing that actually holds the atom together. And that's important because protons, since you have all these protons in the nucleus of an atom, they obviously have the same charge and they would want to repel, but that strong nuclear force, it says it's 10 to the 28th time stronger than gravity. And that's important because it keeps the nucleus of an atom together. That's why the nucleus doesn't explode and send out protons and neutrons all over the place. So strong nuclear force is an extraordinarily strong force. It's the strongest of the forces that we're going to talk about here. Weaker ones would be the weak nuclear, the electromagnetic, and gravity. So the weak nuclear force, it's probably the least talked about one, at least for what we're doing. But it's what causes beta decay. It can affect electrons, but it's just not a real strong force, and not the most talked about one either. One that we do talk about quite a bit would be the electromagnetic force, and it's stronger than the weak nuclear one. And it's the one that really affects a lot of the things that happen around us. The electromagnetic force, anything to do with the electricity and magnetism, comes into play here. Specifically in atoms, it's the stuff that will deal with the chemical bonds taking place, and in interactions where you have electrons being transferred between different atoms. The last one there is gravity, and believe it or not, gravity is the weakest of those forces. It says it's 100 times weaker than the weak nuclear force, right? So in order of strength, right, gravity is the weakest, and then you have the weak nuclear force, then your electromagnetic force, and then your strong nuclear force. So when you think about gravity, we think about it as being really strong because it holds us down, but it's actually significantly weaker than the other forces that we actually have. So just some kind of interesting ideas there on those fundamental forces that make up the world around us. I'm not going to spend a lot of time on this other than just to touch on it because you may have heard of it before, but there are some theories that talk about unifying those forces together as far as where they occurred in terms of the Big Bang. So there's the electroweak theory, the grand unified theory, and this theory of everything trying to link all of those forces together. The electroweak theory, like it says, it's just the weak nuclear and the electromagnetic forces were combined within a billionth of a second after the Big Bang. So again, there's these ideas of how these forces all interacted right at the beginning of our universe. Grand unified theory takes time back even farther, back to 1 nillionth which is 10 to the negative 35th seconds of the Big Bang Theory. And the grand unified theory really hasn't, it's hypothetical. It hasn't worked to combine everything together yet, but that's one of the things that the theoretical physicists are actually trying to do, is to link all those different theories together in terms of what happened right at the beginning of our universe. All right. Well, what is it that makes up our universe? Well, it's elementary particles. So we think about an atom as being the basic building block of matter, but in reality, atoms can be broken down. We talked about that in nuclear fission and nuclear fusion, that atoms can be broken down. So this is where we want to talk about what it is that actually makes them up. So what is it that makes up atoms? Well, we know it's protons, neutrons, and electrons. But are protons, neutrons, and electrons the smallest things? Well, it turns out kind of yes and kind of no. Electrons are actually elementary particles, but protons and neutrons are not elementary particles. They actually can be broken down farther. All right, so what are these things? Well, the first type of elementary particle would be a lepton. So a lepton, it's something that they're not affected by the strong nuclear force. What are those things? Well, they can be electrons, are probably the most common type of a lepton that you've heard of before. There's also things called neutrinos and muons. Neutrinos are actually pretty important because that's one of the things they're actually studying out at the Homestake mine, if you've ever heard about any of the work going on out there. But so when you think about an elementary particle, electrons are elementary particles. We believe them to just be the simplest type of matter that's going to be there. So what are protons and neutrons? Well, protons and neutrons are actually something in a class of particle called hadrons. And hadrons there's lots and lots of different types of hadrons, but protons and neutrons are probably the most commonly known type of hadron. But you need to understand that protons and neutrons aren't elementary particles. There's other things that actually make up protons and neutrons. So what are protons and neutrons made of? Well, protons and neutrons are made of quarks, and protons and neutrons are kind of unique in that they have fractional charges. So if you notice, a proton is actually made up of 2 up quarks and 1 down quark, and a neutron is made of 1 up quark and 2 down quarks. So it's kind of unique in that quarks are elementary particles, but they definitely do have fractional charges. So they're not like protons and neutrons or protons and electrons that have a +1 and a -1. They just have a fractional charge there. One mistake here is that when you add these up, the charge on the neutron should end up being 0. That number's wrong there. It should go -1/3, and +2/3. So that should add up to 0. So that's a mistake on this image. But anyway, when you think about a quark, just keep in mind that quarks are elementary particles, and they're the things that actually make up protons and neutrons. And there's lots of different types of hadrons that can be made using quarks. It's just that protons and neutrons are the most common. So if all those words made your head spin, I apologize. But if you have any questions, please let me know. Have a good day.